Okay, in the first video, at the very end of the first video, or part one of this lecture, you may remember that we found from a set of orthogonal vectors, we had like, let's say V1 through Vn, this was orthogonal. We constructed an orthonormal set of vectors such that their span was the same, right? These vectors generate the same subspace, via scaling Vi by 1 over the magnitude of Vi. We constructed this W1 through Wn, where Wi is equal to Vi over its magnitude, right? And this was orthonormal with same span, right? And so we can construct an orthonormal set with the same span given any orthogonal set, right? Like to find this orthonormal set, we necessarily had to start with this orthogonal set, V1 through Vn. And now let's ask ourselves the question, what about for arbitrary vectors? Like let's let U1 through Un. Well, so arbitrary is unfair. Let's say U1 through Un are linearly independent. So this is a set of linearly independent let's say let U1 through Un be a linearly independent collection of vectors, just to be grammatically correct. Then here's a question. If this isn't necessarily orthogonal, all we have is linear independence, can we find, and if so, how do we find W1 through Wn orthonormal such that the span, and I'm going to shorthand this here and just say Ui is equal to the span of Wi. Okay. I might start doing that just to, because I'm lazy. Mathematicians are lazy, right? So here's the question. If we're not given something orthogonal, but just linearly independent, can we still construct this orthonormal set that is a spanning set? The answer is yes. And how? So and how is by the Gram-Schmidt process. So this is an algorithm, and let's see how this algorithm goes. Let's start with U1 through Un. Let's let this be a collection of linearly independent vectors. And let's say in Rn. Okay. Then what we want to do is we're going to make or construct a set of vectors that has the same span and is orthonormal. So how do we do this? First, so I'll just be a little more rigorous here. To find this collection of vectors Wi orthonormal with same span as Ui, so let's just say this. So here's how we do this. The first step is we're going to inductively define a new collection of vectors. So we're going to construct a new set or collection of vectors, v1 through vn, as follows. We're going to define u1 or v1 to be u1, and then we're going to define v2 to be u2 minus u2 dot v1 over the magnitude of v1 squared times v1. And this sounds like a lot, but if you notice, this is actually just the projection of u2 on to v1, right? So, and then we do this inductively. So I'll show you what I mean with one more step here. So v3 is going to be u3 minus, and then we have u3 dot v1 over the magnitude of v1 squared times v1, and then minus, we do the same thing for v2. So it's going to be the projection of u3 onto v2. So we'll have u3 dot v2 over magnitude of v2 quantity squared v2, et cetera, vn, right? So we do this for every vector u1 through un to get a vector v1 through vn. And the last one, just, and it kind of gives you a generalized formula here, is un minus un v1, un dot v1 over magnitude of v1 squared v1 minus, right, et cetera, all the way up to, the last one would be un dot vn minus 1 over magnitude of vn minus 1 quantity squared vn minus 1. So this seems pretty messy, but it's not that bad, I promise, right? It's just you're subtracting projection vectors here. And when you write out the formula for projection vectors explicitly, it looks a little messy and a little scary. Okay, so what did this get us, right? We're trying to find an orthonormal set that has the same span as the original set of vectors that we started with. Well, what this does is this construction, and it's based on the definition of these vectors, like based on subtracting the projection. What this does is it gives us an orthogonal set with the same span. But then to get an orthonormal set with the same span, we construct W1 through Wn as follows. We say Wi is equal to Vi divided by the magnitude of Vi for all I, for all I ranging from 1 to n, right? And this is exactly how we pass from an orthogonal set to an orthonormal set, is we divide by the magnitude of every vector to guarantee that every vector in the collection is of unit length. And here's the conclusion. So the result. Well, first we have that V1 through Vn is orthogonal. We have that W1 through Wn is orthonormal. And lastly, we have that the span of all three collections of vectors is the same. We also have that the span of U1 through Un is equal to the span of V1 through Vn, which is equal to the span of W1 through Wn. Okay. So this algorithm gives us a way of finding an orthonormal collection of vectors that spans, or the subspace induced by the span of those vectors is the same as the subspace induced by the span of the original vectors. Now, you may ask, we can do this. Fantastic. Why? Why would we do this? Well, here's kind of a very rough picture of why. So why do we care? Or why is it important, right? Well, let's look at R2, for example. We can find a collection of vectors like R2 could be the span of two vectors that are not even orthogonal, like 1, 0 and 1, 1, or something like this, right? Well, then your unit vectors are, well, 1, 0, and then 1, 1. And so your notions of distance and how you measure angles, whatever, in R2 with this basis, right? Because, or with this spanning set, well, these aren't perpendicular. And so notions of distance and things get pretty complicated. And so instead, it's more important, or it's more beneficial to understand spaces and subspaces in terms of perpendicular vectors of unit length, right? And this is how we understand Euclidean space as just being all linear combinations of the vectors in every coordinate direction, right? Like X, Y, Z. And so now let's say we're in R3 here. Like we understand R3 the most intuitively as being the span of I hat, J hat, K hat, right? Which are all, that's an orthonormal basis for R3. And so this is why we care to do this. Okay. So I think what I'm going to do is I'm going to experiment a little bit and break these videos up into more videos, but less time. And so now that we've explored how to find like the Gram-Schmidt process and what this algorithm does, I think I'll let that be a video on its own. And then the next video we'll do purely examples. I think maybe this is a better approach. So next we're going to look at examples of, or how can we actually use the Gram-Schmidt process to find explicitly these orthonormal collections of vectors.